had. 18, excuse me, was just asking you to figure out, can you use this or not? Now, does anybody remember why we do this test? See if it's
binary distribution.
It makes a normal distribution. If they pass both of these tests, they approximate a normal distribution. It approximates your normal curve. If you remember back to those bars, if it was less than that, it was slightly skewed. The higher, the higher it was, the better it was, the more normal it looked. Once we know they passed the test, this already is your mean. So use whatever number you find there. And then your standard deviation is your square root of n times p, which you did, times q. Don't forget to take the square root. Okay? So that's all that was asking you for. Can we use this? Can we not? Now, most of the times, obviously, in these problems, they really should pass the test, or you won't be able to do anything else. So they'll give you the whole problem, and you won't be able to do it. So here you go. Here's another one. A survey found that 67% oppose raising the Medicare eligibility from 65 to 67. You randomly select 80 U.S. adults, you ask them how they feel, blah, blah, blah. Find the probability that the number who oppose raising the age is at least 65. Now, if you wrote your probability statement and you went to use your z-score statement, you would say, where's the mean? Where's the standard deviation? That tells you that this is a binomial distribution. And you had a percentage of people that oppose this, and then you selected 80, and this is your stuff that you're going to go by. And it's still asking for the number who oppose. Make sure that that is the same. Every once in a while, they switch it up. Oh, okay. Okay. So, test. Make sure you do your test first. Test first. Now we have your mean. From there, we can find your standard deviation. Now you have enough to do your z-score. Before, you didn't have this mean or that standard deviation. Now you have both. At that point, you can use your normal CDF. You can put your normal CDF in here as well. The only thing you have to do first is correct this for continuity. You have to correct this for continuity. Can everybody make that correction? Yes. Before you put it in your z-score formula. But at the z-score formula, through that, you can use your normal CDF. Before, actually, your normal CDF will probably even, I'm not sure if this works, but it even might let you do this in here. I'm pretty sure it might let you do that because it lets you do the standard deviation. I mean, if you wanted to put this in, you probably can put everything in here. And then it probably is the most exact. I'm not sure if it does, if it lets you put that in the little pieces.
I put them in the thing, below in the line, in between. I got 10657.
Yeah, but see, you use your calculator. I use the z-scores. So,
is it right still?
absolutely, because we round here to 2 decimals. We find your area, then we subtract your areas. Your calculator doesn't round until the very end. Like, it doesn't hold a 2-digit z-score.
Right.
It has its own method. So, you're very close. Were you 0657?
Yeah.
Yeah, you're very, very close. It's just all in the rounding. Okay, so is everybody okay with this? Now, this was greater than, so you had to subtract your area from 1. Again, this is why your sketch is helpful. 64 is over here somewhere. That's a really small area, right? If I look up my area to be 0.9952, is that possible? No, that tells me 1 minus. That's why I'm big on the sketches. All you need is 1 sketch so that you get a reference. Well, I'd like 1 sketch. Just 1. Do you have to fill it all in? No, but this way when you see 64, isn't it easier now to say, oh, that has to be a very small number?
Yeah, but how would you know if you don't make the sketch? You can't. You wouldn't know if you need to minus it by 1 without the sketch.
You do from this, if it's pointing to the right, if it's a greater than, it's pointing to the right, you know you want your area to the right, you look up your area to the left. But that's what I'm saying. The sketch is much easier because by the time we get through all of this and you get your answer, you went through a lot of work.
Yeah.
So you find this answer, you say, there's my answer.
Yeah.
But when you look at your sketch, you say, oh, that's not possible. So, like, a lot of this does make sense, which is nice in statistics. We don't always see that in the Algebra 2, pre-calc, but we do see it in statistics that it does make sense. Exactly 50, you want your bar that's right here somewhere. You want this bar, exactly 50 would be a little point on that. You want to expand it to a bar. You want the area under the curve for when this is between 49.5 and 50.5. If you never use the calculator for anything else, the in-between is the best. You have a lot of work right here. You can bypass this with your normal CDF. You're going to put your X values in, your lower, your upper. They're right there. Your mean, your standard deviation. It's going to come back, like Nick said, with 0.0657. If the rounding is a little different, we rounded to 2 decimals on your z-score. We looked up those areas, we subtracted them. If for anything else, this guy is nice for the in-between. If it's harder for you to figure out a lower limit and upper limit with a negative 999 and positive 999, this one you don't have to think about it. You have your upper and your lower. God bless you. Okay, and the last one for this part was more than 60. Now, more than 60, here's my 60 over here somewhere. 60.5, whatever it happens to be. So is my area going to be less than 50% or more than 50%? Less than half, right? So again, it tells you that you need to subtract at the end. You're going to need to subtract. More than 60, be careful. You can't use 60. I have to have more than 60. So I have to start with 61, 62, take your low end and drop it 0.5. That's where the 60.5 comes from. I find this really helpful to write it out first, because then it's almost like without thinking. Drop the low end 0.5, raise the high end 0.5. So you put this in, and don't forget to 1 minus that area, because that area is small. Only if you could use 60. If it said this, then I can use 60, 61, then I would go to 59.5. But if you have to have more than 60, I tell you, okay, you can't go on to the next course unless your average is more than 60. What do you have to have? 61. You can't have 60. It has to be more than 60. Yeah, well, yeah, you can have a 60.5. So we're going to start at 61 and drop it to 60.5. Be careful with the equal sign. That makes a difference. Also, when they do the in-between, if they don't say inclusive, it doesn't include it. I think we have one that doesn't have an inclusive in here. And the rest kind of work the same. I know this was a little redundant to go through, but I figured the more you do these, the more you look at their wording. Sometimes they say no more than, sometimes they say at least, sometimes they say more than, they say less than. If you get used to this and comfortable with this, it makes a big difference. So we have 35% of your U.S. workers are college graduates. You randomly sample 500 and ask them whether they are U.S. graduates. And they're going to say yes, they are. No, they're not. So you find the probability that the number that graduated is exactly 175. Look where 175 falls. Right here. Right in the middle here. Okay? Exactly 175. That's a lot. That's a pretty big bar there. Okay, so you've got an in-between setup. First test, obviously this has to work, otherwise we won't have anything to do with the problem. All 3 sections. So we know that it works. We found the mean, we found your standard deviation. Find your point. Of course it's symmetric about your mean because it's 174.5, 175.5. If you use your normal CDF, this is your lower limit. This is your upper limit. your mean and your standard deviation. That works really, really nice in that. Good? And you all remember to subtract your areas, not your z-scores. Okay, never, never, never subtract your z-scores. Okay, I have no more than. This was a different one, the way they said it. No more than 225. That means, can I have more than 225? No, no more than 225. So you have to have 225 or less. So 225 is way up here somewhere, isn't it? All the way off my chart. So to the left, how much area of my curve should I have? About 100%. And this guy, be careful because we corrected for continuity. We put your correction in, not that it's going to make a difference because you're still going to be about 100%. There's your z-score, and we say approximately 100% because there's always a little bit to the right of that. Always a little bit. Your tails on your curve never, never stop. They keep on going. They just never touch that axis. So we need to say approximately. That's the little squiggle line. Approximately 100%. And if you did your chart, like a lot of you were asking me, could I get a z-score over here? If you did your chart, you'd have seen it was way off your chart. Way off your chart. That kind of confirms it. At most, that's the most you can have. 200. This time you include 200. So you're looking at 200, 199, raise it 0.5, find your z-score. Area is to the left. That should be a big chunk of your curve, right? You guys are all good with this? Good. 28. Again.
This is what the majority of the test is going to be?
This is half the test. The other half is the samples, the one with the center limit there with the samples. I know, it seems like a long time ago. I'm going to give you a review. Yeah. All right, again, you test it, you find everything. To area to the right, you subtract it from 1. Are we good? Okay, you get it? It's kind of getting there, right? At most. Here's the one I was getting to, guys. Between 80 and 120, but they didn't say inclusive. So when you make your statement, here's your statement. It's not including those numbers. So I can't use 80. I have to use 81. I can't use 120. I have to stop at 119. So this one you drop down. This one you raise up. So again, a normal CDF works really nice with this one. Try it. If you don't ever use it, try it. Look at all the stuff that you bypass. Your mean, we found our mean. We found our standard deviation. It works really nice. It bypasses all that work.
So it's true for the twos when we add unconstant and lower one.
No. What happens with the in-between, sometimes they use the word inclusive. Inclusive means include. So then it would look like this. And then you'd start at 80, go to 120. You would drop this guy to 79.5. You would raise this guy to 120.5. Well, you do, because look how different you are. You're only like one off. There's a lot of numbers, so your answer is going to be close. I know I would take off because it's corrected wrong. Of course it's going to be close, because isn't it approximately the same space almost? Yeah. But be careful when they don't say inclusive. Then it doesn't include. And like Dan said, he's going to get real close to it. And then your last one. This was a nice one, only because it was a little different the way they worded this. But the whole goal behind this was to see what happens when your sample size changes. Now, your probability statement didn't change. So I want you to think about this. If I have to get at least 30 or more employees that use my public transportation, and I get only 5%, 0.05. Do I have a better chance of getting more than 30 if I only have 100 employees versus 500 employees? I still have to hit the 30 number. So if I don't have a lot of employees, should I reach 30 easier or harder, right? The more employees I have, when I have like 500 employees, but I only want 30 of those employees to say yes, wouldn't that be a better probability? Are you with me? Okay, so it shows how your sample size affects this. Your probability statement stayed the same. Everything else stayed the same, but of course, your mean and your standard deviation changed because of your sample size. But it's a better probability for me to have a lot of employees and have at least 30 of them say yes, that they use public transportation. It would only make sense. If I said, out of this room, only 5% of you walk to school, I'll only maybe get a couple of people out of my 30 kids. Let's say I get 2 kids, 1 kid, 2 kids, whatever. If I test the whole school, 3,000, shouldn't I get a lot more than that? 5% of 3,000? Yeah? Okay? And then the 1,000 obviously has to have a very high percent. Any questions on this at all? This is for your review, so write this down. And let's go through the first one. On page 288, guys, take a look at number 53. This is just going to ask for the mean and the standard deviation of your sampling mean. And then we can sketch. Remember I told you to sketch off your samples. Don't sketch off your population. Sketch off your samples. Because remember this? This has the big one. Then when we take the standard deviation, it made it small like this, remember? And it's very hard to superimpose one onto the other and figure out where all your Z-scores are, because they change. So if you take a look at this one, this was from 5.4. This says the annual per capita consumption of citrus fruit in the U.S. is normally distributed with a mean of 85.6 and a standard deviation for the population of 20.5. Okay. Here's the difference. Random samples of 35 are drawn. Okay. You want to find the mean and the standard error of the mean. The standard error of the mean is your standard deviation for your sample mean. So we said the mean for the sample is the same as the mean for the population. The mean stays the same, but the standard deviation changes. Because why else would they give you 35? They have random samples of 35. So now you can make your sketch based on your sample. If you make your sketch based on your population, then you're going to have to squish this whole thing in, which is a little harder. So use this mean, 85.6, and make your bars to match your sample. Add 3.47, so 89.07. You can just keep adding them down. Use your sample standard deviation to make your sketch. This didn't ask you to do a Z formula. There's no probability statement. It just says find the mean and the standard error of the mean. That's your sampling standard deviation. The next part will ask you your probability statement. I just figured I'll give you one where you just have to say what's different there.